Look up at the night sky. Stars scattered across darkness. Galaxies drifting far beyond what the eye can see. It feels infinite. But is it? For centuries, humans have asked what the universe is made of, how it began, how it will end. But there is a quieter, deeper question beneath all of that. What is the shape of the universe? Not the shape of galaxies, not the shape of space near planets or stars, but the overall geometry of reality itself. At first, the question sounds abstract, almost philosophical. Yet today, scientists treat it as something measurable, testable, observable. And surprisingly, we have learned quite a lot. To understand cosmic shape, we must let go of everyday intuition. In daily life, shape means boundaries, edges, surfaces you can walk around. The universe is different. Its shape is not about what it looks like from the outside, because there is no known outside. Instead, the shape of the universe is about how space itself behaves on the largest possible scales. In modern cosmology, there are three broad possibilities: a flat universe, an open universe, and a closed universe. Each describes a different geometry of space. Each leads to a very different cosmic destiny. Let's begin with the simplest idea: a flat universe. In a flat universe, space follows the rules of familiar geometry. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees. If you could travel in one direction forever, you would never loop back to where you started. Space extends endlessly, without curvature. But flat does not mean thin. It does not mean two-dimensional. It means space is balanced, neither bending inward nor outward. Next, an open universe. In an open universe, space curves outward, like the surface of a saddle. Parallel lines slowly diverge. Triangles have angles adding up to less than 180 degrees. Such a universe expands forever. Matter thins. Galaxies drift apart without end. Time stretches on, colder and darker. And finally, a closed universe. Here, space curves inward, like the surface of a sphere. Parallel lines eventually meet. Triangles have angles greater than 180 degrees. If you traveled far enough in one direction, you would eventually return to your starting point. In this universe, expansion might one day slow, stop, and reverse. A cosmic collapse. A return to density and heat. Three shapes, three futures. So which one do we live in? To answer that, scientists turn to the oldest light in existence, the cosmic microwave background. This faint glow fills all of space. It is the afterimage of the universe when it was just 380,000 years old. Long before stars, long before galaxies, before planets or life. This radiation is remarkably uniform, almost the same temperature in every direction. Almost. Tiny variations, 1 part in 100,000, are frozen into this ancient light. And those variations carry a message. They are imprints of sound waves that rippled through the early universe, pressure waves moving through a hot, dense cosmic plasma. The size of those ripples is known. Physics predicts how large they should appear, but how large they do appear depends on the shape of space. In a closed universe, light paths curve inward. Those ancient ripples would appear larger than expected. In an open universe, space curves outward. They would appear smaller. In a flat universe, they appear exactly the size predicted. When satellites mapped the cosmic microwave background with exquisite precision, the result was startling. The ripples were exactly the expected size. Within the limits of measurement, the universe is flat. Not approximately flat, but astonishingly close to perfect flatness, balanced to within a tiny fraction of a percent. This result raised another question. Why is the universe so finely balanced? According to theory, any early deviation from flatness should have grown dramatically over time. Yet the universe remains poised on this cosmic edge. This mystery led to the idea of cosmic inflation, a brief moment just after the Big Bang when space expanded exponentially fast. Inflation would stretch any initial curvature until space appeared flat, just as the surface of Earth looks flat if you stand on a small patch. But the cosmic microwave background is not the only clue. Scientists also study the large-scale structure of the universe, the distribution of galaxies, clusters, vast cosmic voids. On the largest scales, matter traces a web-like pattern, filaments and nodes shaped by gravity over billions of years. The way this structure grows depends on geometry. Measurements of galaxy clustering, gravitational lensing, and cosmic expansion all converge on the same conclusion. Space behaves as if it is flat. Yet there is an important caveat. Flat does not necessarily mean infinite. Topology, the way space is connected, could still be complex. The universe could be finite but unbounded, like the surface of a sphere but in higher dimensions. We may live in a cosmic space that loops back on itself in subtle ways we have not yet detected. So what do we actually know? We know the observable universe behaves as though it is flat. We know this with remarkable confidence. But beyond the limits of what light has had time to reach us, we do not know. The universe may be far larger than what we can see, or it may wrap around itself beyond our horizon. Its true global shape could be simpler than we imagine, or profoundly strange. In the end, the shape of the universe is not just a geometric curiosity, it is a clue to the deepest laws of nature, to the earliest moments of existence, to why the universe is the way it is at all. For now, the cosmos appears balanced, neither collapsing inward nor flying apart uncontrollably. A universe balanced on geometry, and in that balance we continue to look outward, measuring, listening, trying to understand the shape of everything we will ever know.